You don't go to Okay, so today we're going to discuss electromagnetic induction or Faraday's law, which I think is chapter 29. Okay?
Actually, not a bad idea.
And we have a few worksheets on this chapter where we do the bulk of the project. I think 3 or 4 worksheets on it, and each worksheet, you know, there are several projects. A lot of projects that we're going to be working through individual worksheets. Okay, so I want to introduce Faraday's law today for electromagnetic induction. But before I introduce Faraday's law, we're going to do two problems. A problem that's needed to do the next problem, and then show you that we can explain everything without needing Faraday's law. Okay? And then we will make a twist to it, and then actually Faraday's law then is required. Because there is something that we can explain without. Okay? So first, I'm going to discuss the concept of motional EMF. Motional EMF. Motional EMF. Yeah. They should be there. Yeah. So here is a conductor, aluminum. And imagine there is a magnetic field toward the front of the classroom. Magnetic field towards the front of the classroom. And here is the rod. The rod will have length L. Okay. And there is a magnetic field into the cage. Okay. So let's just have our x-axis, our y-axis, and the magnetic field is into the cage. So magnetic field is A. I'm just trying to figure where to draw it. I know I drew only one, but imagine there is magnetic field everywhere, and it's toward the front of the classroom, into the cage. Okay? Is that clear? So let me write down the magnetic field then. Minus P and then K hat, right? It's in the K hat direction into the cage. So here is the rod. That's the rod. And the rod is not moving. Does anything happen? No. No, if the charges are not moving, the magnetic force on them is 0, right? Magnetic forces are there if they would happen if the charges are moving, right, in a certain direction. So imagine now I pull this way. So as I carry the rod this way, this conducting rod, then we ask what happens. So somebody is pulling it to the right, and we ask the question, what happens? So that's the motional part, motional EMF. So it's EMF that's created because of the motion. So somebody pulls the rod. Okay? So as we pull the rod, imagine I take a small charge, a little positive charge here. Here's a positive charge. Positive charge. So now it has a velocity v this way, right? Charge with a velocity v, because I'm dragging the rod this way. It has a velocity v this way. So what happens to it? For that one little charge? It will experience a force in the upward direction. Good. Yeah. So the magnetic force, FB, is Q E cross B, right? So the magnetic force would be in the positive y direction. Let's see some positive. Yeah.
No, I'm good.
No. Good. So there will be a magnetic force in the positive y direction. So charges, plus charges, will migrate up, right? And if it's a negative charge, it will go down. We experience a force in the downward direction. So if all the pluses, they start going up, what happens to the top end? It becomes positive. So we have pluses, right? A bunch of plus charges. And this side will become negative, right? Minus. This is supposed to be plus. So as long as you're pulling, the charges will separate. The pluses will go up, the minuses will go down. Will that go on forever? So you keep pushing, you keep pushing that way, pulling, and the magnetic field is into, and the region is long, so you can run forever. And so, will the positive charges keep migrating up? And then, is there a limit to how many I can pile up there? No or yes? Will they have had enough at some point? Yeah.
Like eventually, the charges on top they're gonna have an electric force that pushes them.
Good. There will be an electric field in the downward direction. And so, yes. So in addition, eventually, right? So let's say at some point they will stabilize. When does that happen? Well, you got your magnetic force upward, right? There will be an electric force downward, electric. And when they're equal to each other, the charges will stop migrating. You have had enough. Is that clear? Okay. So they will stop moving when the electric force, the magnitude of the electric force equals to the magnitude of the magnetic force. This one. The magnitude of the magnetic force is just Q dV, right? Q dV is the magnitude of the magnetic force. So when these two are equal to each other, electric force is QE, isn't it? And the magnetic force is Q dV. So the electric field is the magnetic field times the speed. Clear? That's the magnetic. That's the electric field. So there will be a potential difference between the minus n and the plus n, wouldn't there? It's a potential difference. And we know how to find the potential difference. By definition, right? So first, let me write down the electric. The electric field is minus E J hat, right? The electric field is in the downward direction. Its magnitude is E, but it's in the minus J hat direction. And E is dV. Alright. Now, what's the potential difference between top and bottom, between the plus and minus? So let's say this is y equal to 0. This is y equals to L, right? That's the length of the rod. So the difference in potential difference. This is V for potential difference. I'll put bars so it's potential difference, not speed. Minus E like that. Right? Definition of potential difference. DS, in our case, we're finding along the y direction. So that's dy j hat, right? What's their dot product? E dot ds. So it could be what's the dot? Right. So here I would have minus pv dy, right? Minus pv dy. But there is a minus sign, so it becomes what? Just pv dy, right? We have y from 0 to L. So this just becomes V times L times V. That's the potential difference between the minus and the plus. It makes sense. The positive should be at the higher potential. So VLV. Is that clear? So it's like you have a battery. You have full of charge there at the plus and full of minus charges there. If I somehow connect them with a wire, what happens? If I make a wire to complete the circle. Yeah, what happens? Oh yeah, I like that. Yes. So current will flow. The pluses, they will start coming here. In this case, they have nowhere to go. They just get to the edge and they have nowhere to. They can just jump out of the conductor. They're bonded to it. So if you provide a complete loop, then they will start to circulate, and you will have a counterclockwise current. Okay? So that's my next step. So as long as I'm pulling, I will separate the charges that way. As long as you're pulling. Okay? It acts like a battery. And the potential difference of that battery is this. If you want it 10 volts, just run faster. Okay? Make V larger, or make the magnetic field bigger, and then you will have a stronger EMF, a stronger potential difference. Okay? So let's do exactly that. Can I do that? Start that here. I'm motivating Faraday's law. So far, we didn't need a new law. We're explaining everything using what we know. So the next thing is we're going to, here's this rod. Here's the rod. Same rod. Okay. We're going to connect it on a circuit. I'm going to draw like rails here so that when I slide the rod this way, it will not lose contact and you will always have a complete circuit. And here is, I'm going to connect here some resistor R. The magnetic field is in. It's in everywhere, right? Magnetic field, just like earlier. And we're going to pull with a circuit force, and the velocity is going to be V to the right of the rod. Seems too silent. Any questions? Is it obvious? No. Okay. So what's not obvious? What's the issue? What's the question? Or should we go back? Yes.
The magnetic field is going in.
Magnetic field is in.
Yeah. And that's across the entire.
Yes. Everywhere it's in. So.
Is that a rod?
Huh?
Professor, is that a rod?
This?
Yeah.
That's the rod. Yeah, that's the same rod. And now I made a circle.
So it's connected to the wire?
It is connected to the wire. Yes. It's connected, but it can slide.
Oh, it can slide.
So I can make the rod bigger. Go to the right.
Okay.
I thought I saw a hand somewhere. No. So now, what's the potential difference across this resistor? IR. Yeah, the current. IR would be the potential. But in terms of what I had earlier.
EL.
Yes. That's BLV, is the potential difference across this resistor. And we would have a current. We go this way. So this is called Ohm's law. Okay. So I is delta V over R. So it's BLV over R. That's the current. So that's how much power is consumed by the resistor.
IR squared.
I mean I squared R.
Oh yeah, I squared.
So I squared, you square this and multiply by R. So it becomes B squared, L squared, V squared. R squared on the bottom, but you have one R on top, so it just becomes an R on the bottom, right? What's that? Good. Still good. We're okay. And then I want to know the magnetic force. Yeah. let's figure out the magnetic force now. So first of all, the charges would be going counterclockwise. So here is a plus charge. The plus charge is part of the rod, so it has a velocity to the right. And it's also part of the current, so it has a velocity upward. Right? So the velocity to the right is V, just the letter V. And then the velocity upward, I need to give it a different name. I'll call it U. Okay? I'll call it U. That's the velocity. That's Y. The velocity. So what's the total velocity? Okay, so V I hat plus U J hat. Right? So what's the magnetic force then? So let's say the charge is Q. So it's going to be Q V total, right? Crossed with the magnetic field. QVB. QV cross B. So let's write that down. So I'm imagining I have a little cube that's moving. I would call it dq later, but for now I'm just going to call it q. It's a hassle to keep writing dq. Later I'll call it dq. So I get q. The total velocity is v I hat plus u j hat cross product with b, but b is minus b k hat. Yes, it's a good time to review or to just, yeah, I guess re-emphasize on cross products. What is I hat crossed with k hat? Almost j hat. Negative j hat, yeah. I hat cross k hat is minus j hat, but there is a minus sign, so it becomes just positive j hat, right? So you would get this. QE, then V becomes j hat. I hat cross k hat is minus j hat, but then there is a minus that becomes a plus. How about j hat cross k hat? So just the j hat cross k hat is just I hat, yeah, is I hat, and then there is the minus sign, becomes minus I hat. So minus u I. So that's the magnetic force. It's the magnetic force. In other words, the magnetic force would have a positive y component and a negative x component. Magnetic force would have two components, one of them is plus, the other
Is the rod connected to the circuit?
yeah, the rod is connected. That's why there is current.
So is it connected, right? Like does it conduct?
That doesn't work.
Conduct? Is it actually
Yes,
wire?
yeah, the rod is an actual conductor.
okay.
Yeah. So earlier, we just did the rod by itself. It was connected to nothing. So you just had the plus and minus. They just go here. But now, the plus is when they get here, there is a cap. They can go around. Okay, so that's the magnetic force. Now, I would like to know how much work is done by this magnetic field. Zero. But let's prove this, right? In this case. So the magnetic field will do zero work again, yeah.
Why is the U is going upward?
Because the charges, they're moving to the right, along with the rod,
Yeah.
and there is a current, so they're moving up the rod also.
Also, it based on the direction of the current?
The charge, yeah, that's the total velocity of them, right? So imagine you have a positive charge here, right?
Yeah.
It's part of the current, so it must have some velocity upwards along the wire.
But it doesn't have like the positive and the negative sides. I mean, like the potential difference.
Yeah, that's fine.
Wait, that's fine. Because I thought like charge is
doesn't have-
flowing from higher to lower.
Yeah, so the, oh, okay, so that's clear though, the U and the V.
No, I mean.
I thought your question was about why is there a U? So is
Yeah.
that clear?
Yeah.
Okay, so now your next question was, is there a pluses here?
Yeah.
Okay, so every time you would get a plus charge here, there'll be a plus charge behind it, and another plus charge behind it, so there is always a force upward, so the charges would be moving this way, in the counterclockwise direction. So you never, because they're connected, earlier it wasn't connected, so they couldn't pile up there. But now they cannot pile up, they will just flow.
Oh.
So everything is a conductor. So that's the magnetic force, and I would like to know the work done. Yes, the easy way out is the work done is 0, and we can just move on. But let's not. Let's actually do it and figure out that the work done is 0. What's the definition of work?
Force.
F dot dr? Okay, so the work done, I'll put dW, the work done by the magnetic force, dWB, the work done by the magnetic force, is the magnetic force dot dr. By dr we mean the displacement of a single charge, right? Dr. We're just checking how much work does the magnetic field do on one little charge. And then we would worry about, if the work done on every little charge is 0, then the work done on all the charges will be 0. Yeah. So, okay. What's the magnetic force? It's that. Q, B, D, J hat minus U, I hat, right? That's the magnetic force. Dot dr. What's the displacement? Well, it's this. You can write it as dr dt dt, right? Dr dt is what? The displacement, or is the velocity of a charge. What's the velocity of a charge? Is it v, is it u, or both? Yes, it's the total distance. It's u I hat, sorry, v I hat plus u j hat. So u v j hat minus u I hat dotted with, this is dr dt, that's the total, this one. V I hat plus u j hat dt. Okay. Well, j hat that I hat is 0. This is dot product now, not cross. Okay? I hat and j hat are perpendicular to each other. Then j hat that j hat is 1. So I would just get VU, right? Or UV. UV. And then minus UV. I had that I had is 1. So UV. And that's it. I had that J hat is again 0. So this is how much? 0. 0. 0. So alright, so no surprise there. So that's good. The magnetic work, the work done by the magnetic force is 0. So who is doing the work then? We said earlier there is power dissipated in the resistor. The resistor is consuming energy as a function of time. It's consuming a number of joules per unit of time. Those number of joules per unit of time are not coming from the work done by B. They're coming out from the work done by somebody else. Who is that? Which one? Which one? Fe. Not quite, no. In this case, we're not, the charges are moving, so they're not piling up there. Yeah. So who is, huh? The resistor is consuming energy. So somebody has to provide it with that energy. But the potential difference is because because, no, I would say no, because I almost gave away the answer. EMF? But the EMF doesn't just exist by itself, right? There is no battery or anything in this case. Yeah, what did you want to say?
Isn't it just the motion and you pushing?
You pushing, yeah, that's the key word, you. The person, whoever is pulling the rod, you're doing the work. You. So, the external force, let's say. Okay, the external force. So let's look at the rod again. So the work done by the external force over time needs to match the power by the resistor, right? So that we have conservation of energy. So here is the rod. Let me draw the rod by itself. It is still part of the circuit, but I'm just going to draw it by itself. There is the external force this way, right? There is a force backward. What's that force? It will be the X component of the magnetic field. Remember, of the magnetic force. The magnetic force has QBV in the Y direction, but it has this component in the X direction, QBU in this direction. So it's QBU in this direction. That's the X component of the magnetic force. Okay. And these two have to be equal to each other. Why? What's stationary? The rod is moving. Not stationary. Almost. They're not a Newton's third law pair. They don't result from the same interaction, right? There is an easy reason. How fast? What's the acceleration of the rod? Yeah, it's not accelerating. The velocity is constant. Right? It has an x component of velocity, and it's v. So no acceleration means the net force is zero, at least in the x direction. So yeah, so the two forces, the external force needs to equal to that. Okay, so let's try it. So I get the external force, external is equal to Q B U. That's the external force needed to just for one charge, right? But I want through the whole rod. There is not just one charge. So that's where I want to get to the dq part. So I'll put here df is equal to dq, and then b times u. Okay. U is the velocity of the charges up the rod. U is the velocity of the charges, right, along the rod. So that's dy dt, right? Yes. V, the horizontal velocity is dx dt. The y velocity is this one is dy dt. So it's going to be, if we look like this, dq. I'll put u here. It's dy dt, and then v. Let's look now. What's dq dt? I. Okay, so let's find the total force on the whole rod. How long is the rod? L. So we need to integrate from 0 to L, right? What happens when you integrate from 0 to L? It's going to be I, B, what? L. Okay. When you integrate this from 0 to L, you just get L, right? So it becomes I, B, L. That's the external force. Oh, I forget to put this. So, what was I? What's the current? What's the current? This one, right? That is the current in the circuit. So it's going to be BLV over R times BL. So it's going to be what? V squared, L squared, V over R. That's the external force. Okay. So F dW, the work done by the external force, is equal to F external dx, right? It's in the x direction. That's the displacement. Let's divide both sides by dt. What's dx dt? That's v. Yeah. V, right? Which velocity? Right, the x velocity. V, not u. V. dy dt is this one. This one. This one is v. So it's going to be F external times v. Here's F external, and you multiply it by v. What do you get? Yeah, you get b squared, L squared, v squared over r. So the rate at which the external force is doing work, you're doing the number of joules per second by pulling, and those number of joules per second that you do by mechanically pulling the rod, they are equal to the power consumed, or the number of joules consumed by the resistor. So everything matches. Okay? Everything matches. Okay? So no need for Faraday's law to explain anything. I'm going to do a demonstration. Just something similar to that, right? I don't have a uniform magnetic field that's into the page, and I don't have a rectangular loop that, a rectangular loop that looks like this. I just have a circular loop, very circular loop. And this is a magnet. I will just hold the magnet here. I hope you can see from there. This is a galvanometer, and it measures current, detects current. So right now, you see the needle, it's not moving, so there is no current. Here is the magnet. I can bring it closer, there is nothing. This is a coil, and it has 3,400 windings. So imagine it's, instead of just having one loop, I have 3,400 loops. It kind of amplifies the effect. So let me connect this, connect this. So if I can move the loop, right? So let me get the magnet away. I can move this loop, and when I move the loop, the charges, every little bit of charge within the loop will be moving, and so if the charges are moving, we can say QVB, and then there is that force from the magnetic field that pushes the charges up the wire, right? And we can explain that. So here is, here's my, can you see that the needle is moving when I do this? At least, I don't know, probably far. Can you see it? So we can explain this using that approach. No need for Faraday's. Here's where the problem occurs. The charges are at rest. Everybody is not moving. Right? Nothing is moving. I'm free to bring, instead of bringing the loop to the magnet, I can move the magnet relative to the loop. And now I see this. So how can we can't explain what's happening here using that approach. Because that approach requires the charges to already be moving relative to the magnet, or to be moving in my reference frame. But this magnet is moving, so what did start the charges to move in the first place? Because magnetic forces can only happen if the charges are already moving, right? I need the charges to be moving in order for them to experience the force. If they are already not moving, they should never move, according to what we know so far. By the way, we can also be more quantitative. I have a voltmeter here. And we can plus minus on that. So this is the voltmeter. I don't know if you can see the numbers or not. About 0, right? How about now?
Oh.
Yeah. You can have, right? So what you need is not that the magnetic field is strong. I can bring the magnet and make the magnetic field as strong as I can by bringing in the magnet to the middle of the loop. But then there is nothing, right? Because nothing is changing. You need something to change. And that thing that changes is called that we need, that Faraday's law talks about, is the change of flux, or magnetic flux. So imagine the loop has an area. There is a magnetic field that is going in, that wants to go into the area. And the closer I get it, the flux that's going in will get stronger. Or the farther I get it, the less flux is going in. Yeah.
The area is just whatever is enclosed in
Yeah, it's this area in this case. And so we will define flux. It's going to be the same definition as that of the electric field, or very similarly defined. We'll talk about just the units of it. What do you think the units would be for magnetic flux? What was the electric flux definition? That was the right-hand side of Gauss's law. But the flux itself.
How much
EDA, E dot dA integral, right? So basically it was electric field times area times the cosine of the angle. Right, so basically the units are electric field times area. Magnetic flux is going to be similar. It's going to be magnetic field times area. Okay? Magnetic field times the area. And so let's define that. And then write down Faraday's law. And then apply it to this same example. And then we'll apply it to examples where you can't do using this one. Okay? So, magnetic flux. It has the symbol Pb. I would use phi, capital Phi, but we use but here we have to be careful. We have to distinguish electric flux from magnetic flux, right? Here we're talking about magnetic flux. It's, in general, it has this definition. It's B dot dA, like so. In special cases, if the magnetic field is uniform, if the magnetic field is uniform, yeah.
Is it a closed or open loop?
Open.
Oh.
Yeah. Yeah, it has to be an open integral because I will come back to the closed. If it's closed, it will actually be identically zero.
Oh, okay.
Yeah. I'll get back to it. So open integral, if the magnetic field is uniform throughout the area, then this reduces to just B dot area. And that's B A, and then the cosine of the angle between the area and the magnetic field. Okay. So if I have my magnet, here's north, so the magnetic field is comes from the north, right? Like this. So the flux is going in, right? In this case, I would have maximum flux or minimum flux going through the area. More flux, most flux would be going through the area.